All right, linear algebra, lecture 5. And what we've been studying is linear independence, bases for a vector space, and today the dimension of a vector space. So these are very, very, very fundamental notions in linear algebra. Let's just review a little bit. So we say that a list of vectors v1 up to vn is linearly independent if the only linear combination C1, V1, C2, V2, and so forth up to Cn, Vn equal to the zero vector is the only way a linear combination is zero is when all of the coefficients, all of the coordinates are equal to zero. We say that a list of vectors spans a subspace W of the vector space V, and of course W could be all of V, if every vector in W is a linear combination so the same list, V1 up to Vn, is a linear combination of V1 up to Vn. And a basis for a vector space V is a list of vectors V1 up to Vn that has both properties. It's linearly independent and spans the vector space. So the fundamental example of a basis is in the vector space V equal to Fn. F is the field, so F is equal to the reals or the complex numbers. The standard basis is the set of vectors, the list of vectors with one coordinate equal to 0 and all the other coordinates, one coordinate equal to 1 and all the other coordinates equal to 0. This is often called E1, E2, and so forth up to E sub n, but in calculus, that in advanced calculus, certainly in Calc 3, this is what you would have seen. So for example, E1 equal 1, 0, and E2 equal 0, 1 is a basis for F2. But of course, it's not the only basis. There are many bases. If we take V1 to be the vector 1, 2, and V2 to be the vector 3, 5, this is another example in the book. This is also a basis for F2. And how would you prove such a thing? Well, these are two separate bases. So for example, if we take the vector x equal x1, x2, you can easily write this as a linear combination of E1 and E2. Because you can write this as x1 comma 0 plus 0 x2. And that, because you add coordinate wise. And x1 comma 0 is x1 times 1, 0. And 0 x2 is x2 times 0, 1. So here an arbitrary vector in F2 is a linear combination of 1, 0 and 0, 1. Right? So it's easy to check that this list of two vectors is a basis. Is there a question?
What about A3?
I'm sorry. Is there a question?
Yes, what about A3?
This is an F2. There's no E3. This is F2. In Fn, you have n vectors. When n equals 2, you have 2 vectors. There's no E3 in this vector space.
Okay.
Right? Right? I mean, 0, 0, 1 is not a vector in F2. Right? What about this potential basis, 1, 2, and 3, 5? The question is, do there exist scalars? I'll call them C1 and C2, such that an arbitrary vector x1, x2 is C1 times the vector 1, 2, and C2 times the vector 3, 5. Right? That's the question. So here, x1 and x2 are given, C1 and C2 are the unknowns. Of course, this is the same as saying C1, 2C1 plus 3C2, 5C2. And then when you add, you get C1 plus 3C2, 2C1 plus 5C2. So we want to solve the equations C1 plus 3C2, comma 2C1 plus 5C2 equals x1 and x2. Can we find C1 and C2 that satisfy this vector equation? But of course, vectors are equal only when their coordinates are equal. So C1 plus 3C2 has to equal x1, and 2C1 plus 5C2 has to equal x2. So we have to solve these two linear equations in two unknowns. So however you want to do it is certainly up to you. You can take first equation and multiply it by 2, and take second equation and just leave it the way it is. And when you subtract, you get C2 is 2x1 minus x2. And then from the first equation, C1 is x1 minus 3C2. So that's x1 minus 3 times 2x1 minus x2. So you have x1 minus 6x1, that's minus 5x1, plus 3x2. So if I've done this algebra correctly, let's just check. If I take the vector 1, 2 and multiply it by C1, which is minus 5x1 plus 3x2, and I take the vector 3, 5 and multiply it by C2, which is 2x minus x2. Let's actually do it and see what happens. We'll take this vector and apply it by the hour,
We can see.
minus 5x plus 3x2
Professor,
minus 10x1 plus 6x2. Is there a question?
yeah, we can see the page. Yes, okay.
Okay. Plus this, which is plus 6x1 minus 3x2, comma, 10x1 minus 5x2. And when I add coordinate-wise, these cancel, I get x1, these cancel, and I get x2. So it works perfectly. This linear combination of 1, 2, and 3, 5 gives me the vector x1, x2 for all x1 and x2. Right? All right. And last week I proved some important properties of bases. First was an equivalent condition for a basis. So a list of vectors v1 up to vn is a basis for a vector space V if every vector V in the vector space has one and only one. That means has a unique representation as linear combination v1 up to vn. So this is equivalent to saying the vectors v1 up to vn are linearly independent and span the vector space. For one thing, if c1 v1 plus c v2 and so forth up to cn vn equals 0, then the fact that 0 times v1 plus 0 times v2, take the linear combination for the coefficients equal to 0, that also gives the 0 vector. And because every vector has a unique representation, this implies that all of these coefficients are 0. C1 is 0, C2 is 0, and so forth, up to C sub n equals 0. So this immediately implies that the vectors are linearly independent, and of course they span because every vector is a linear combination. And very important is the result that, so this was, I'll call it as a theorem, but this is 231 in the text on page 40. Every spanning list of vectors in a vector space V contains basis. So if you have a sequence of vectors span the vector space, you can remove some of them, and what's left will be a basis for the vector space. And recall that a vector space is finite dimensional if it has a finite spanning set. That means there's some, you may not be able to write it down, but there exists a finite list of vectors such that every vector in the vector space is a linear combination of the vectors in the spanning set. And then it follows from this result that every finite dimensional vector space has a finite basis. you just take your finite spanning set. There's some vectors you can weigh, you don't need them. And what's left will be this.
Excuse me, Professor.
Yeah,
You're lagging a bit, so it's kind of hard to follow what you're explaining.
I'm
the
sorry.
lesson.
I didn't understand what I am doing what?
Your connection is not that good right now, and it's kind of hard to follow what you're explaining for the lesson.
You mean
Yeah,
the
your
audio
voice
is not
sounds
good?
very choppy when you speak.
Like your audio, like when you're saying something, it kind of cuts out a little bit, so it's kind of hard to follow.
Oh, that's interesting. Because Verizon came yesterday and installed what's supposed to be their latest, best, most powerful router. So the signal strength would be good, but
Yes.
so there's nothing I can do about it, of course. I mean, that has to do with the internet connection. The only thing I can hope is the recording is okay. And the recording on YouTube as soon as the class is over.
Okay, Professor. I just want to let you know that.
Yeah, thank you.
Yeah, it's very hard following what you're saying. Everything's broken up.
Oh, okay. But I can hear okay, so I'm surprised the audio isn't as good and as bad in one direction as in the other. But okay. Huh. All right, sorry about that, but the only other saving grace is that I am trying to follow the book very closely, and so everything is in the text. So the last remark, which I also talked about last Wednesday, is the following. So in the text, this is 233. Every linearly independent set of vectors or list of vectors, which is the word the book likes to use. In V and be extended to a basis of V. So suppose V1 up to Vn are linearly independent. This is a finite dimensional vector space. So let me just follow the notation. This is U1 up to U sub M. So those are M linearly independent vectors in the vector space. But every finite dimensional vector space has a base. Let V1 up to Vn be a basis for V. So if I take all these vectors together in the following order, U1 to U sub M, followed by V1 on up to V sub N, this set spans the vector space because just the set of V's spans the space. And our procedure to construct the basis from a spanning set is to one by one take the first vector, keep taking vectors so long as they're linearly independent. When you get one that's linearly dependent on the previous ones, you delete it. So if you go step by step, you won't throw out any of the first M vectors because we know those are linearly independent. But then you might delete some of these and you'll end up with a basis. So this is the idea of the proof of this result. Okay. We also talked about direct sums. So you know that So if you have a vector space V with subspaces U and U, the sum of subspaces U and W is, you can write it like this, you write U plus W. This is the set of all vectors. That's a vector in U plus a vector in W. And you look at all sums for all U and U and W and W. And then we check that this is a subspace of V. It contains 0, is closed under scalar multiplication, and is closed under vector addition. And the sum of two subspaces U plus V, it's called a direct sum if there are two equivalent definitions of this. Let me see which one. Write it down first. So if the only vector in U and V together is the 0 vector, that is the intersection of the subspaces, we know that every subspace must contain the 0 vector. And if you have two subspaces whose intersection is only the 0 vector, then the sum is a direct sum. And every vector, the sum is uniquely the sum vector in U and a vector in W. And so statement about direct sums is as follows. So this is really quite important from the point of view of geometry. This is 2.34. So suppose V is a finite dimensional vector space. U is a subspace of V. There is, or there exists, there is a subspace W of V such that V is U direct sum W. So what this means is, given a subspace U of V, you can find a kind of complementary subspace W such that every vector in V can be written as the sum of a vector in U plus a vector in W. And this is a direct sum. So every vector in V is has a unique representation as the sum of a vector in U and a vector W. And the proof of this goes follows. So if V is finite dimensional, so is their subspace. So let U1 up to U sub M be a list of vectors, which is a basis for U. This extends to a basis for the whole vector space V. That is, we have vectors U1 up to U sub M, and then vectors also W sub 1 up to W sub N, so that this list is a basis for the whole vector space. And let W be the span of these vectors we just added, that W up to W sub n. So every vector in V, a linear combination of the U's and the W's. So V is certainly the sum of U plus W. Only have to show at the intersection of U and W the zero vector. So if there's some vector V, which is in U intersect W, then U is some linear combination of the basis for U, U1 up to UM, and it's also a linear combination of the basis for W. So if you take this and subtract this, since they're equal, you get 0. A1 U1 plus AM UM minus
I mean,
this.
usually you don't really have to, like, 3 years trumps A+ certification. So you might not even have to review that.
I'm sorry, say that again, please.
Yeah. It's better just to go after the other certifications because people let these expire all the time because these are entry levels. So like even King, like the only reason King redoes it is because he has to for us.
I'm sorry, I
It
can't
was up to him.
understand.
He heard him. He was like, I got everything in less than 2 months. I'm like,
You have
okay.
to move in.
Okay. So this would be a linear combination of the U's and the W's equal to 0. But the U's and the W's together are a basis. So the only way this is possible if all of the coordinates A1 up to AM and B1 up to BN are 0. Okay, so this is what we talked about last week. And the lesson for today is chapter 2, section C, which is on dimension. And we will be able to say what is the dimension of a vector space. So our intuition would say that Fn sort of should have dimension n. Right, so R2 or F2 should be two-dimensional. And F3 or R3, this should be three-dimensional. So and how do we make this intuition precise? So theorem 2.35 says that any two bases for a finite dimensional vector space have the same, well, length, which means the same number of elements. So if you have a vector space and you take a basis for it, well, there are many bases. There typically will be infinitely many bases. No matter what basis you take, they have the same number of elements. And for finite dimensional vector spaces, the proof is very simple. It's based on the fact that every spanning set contains a basis. So let B1 and B2 be two bases for the vector space. So B1 is linearly independent because it's a basis, and B2 spans V because it's a basis. So the number of elements in B1 is less than or equal to the number of elements in 2. Because an independent set has at most the number of elements as any spanning set does. But this is symmetric because B2 is a basis, so B2 is linearly independent, and B1 is a basis, so B1 spans the vector space. So the number of elements in B2 is less than or equal to the number of elements in B1. So if you have two numbers and each is less than or equal to the other, then they have the same size or the same cardinality, same number of elements. So in a finite dimensional vector space, the number of elements in a basis is an invariant. It doesn't change no matter what basis you pick. So this gives us the fundamentally important definition of dimension. In a finite dimensional vector space, the dimension of the vector space is the number of elements or the length in a basis. And this is independent of what basis you choose, because we just showed that all bases have the same number of elements, and the notation for dimension is simply DIMV. This means the dimension of the vector space V. So for example, the dimension of the vector space Fn is n, because, for example, standard basis has n elements. What about polynomials? Remember the vector space P sub m of f. This is a set of all polynomials of degree less than or equal to m. And this has a basis of just the powers of z, including z to the 0, 1, 1z, z squared, z cubed, up to z to the m. This is a basis for the polynomials. Every polynomial of degree at most m is a linear combination of these vectors. And one other property of vector spaces is the following. If U is a subspace of the finite dimensional vector space V, then the dimension of U is less than or equal to the dimension of V. For one thing, you can take a basis for the subspace U extend it to a basis for V. So clearly the number of elements in the basis for V is at least as large as the number of elements in the basis for U. So this notion of dimension, it might seem a little bit abstract, but in linear algebra, this is really the most concrete things there is. A simple number of elements in a basis. And given a vector space, problem often is compute the dimension, find a basis, and then count how many elements are in it. So for example, x minus 5 and x minus 5 squared, these are three polynomials in P2. P2 of F. This is all polynomials of degree of most 2. And I claim this is a basis. So why is it a basis? So the dimension of P of F is 3. And here we have vectors. So it's enough to show they're linearly independent. So suppose some linear combination of these is A times 1 plus B times x minus 5 plus C times x minus 5 squared equals 0. Show A, B, and C are all equal to 0. Okay. So I'm going to pause for a moment and give you a chance to do that. And then I'll come back in a minute or two and see how it goes. So what's the secret? Expand this and write this as a polynomial. Get A is bx minus 5b. See, x minus 5 squared is this. So when you collect the terms, you have cx squared. The coefficient of x is b minus 10c. And the constant term is a minus 5b plus 25c. All of that's supposed to equal 0. But a polynomial is 0 only when all the coefficients are 0. So c is 0, b minus 10c is 0, and a minus b plus 25 is 0. We have c is 0, but according to this, b is 10c, but c is 0, so that's 0. And this says a is 5b minus 25c, but b and c are 0. So this is 0. So the only linear combination of these three polynomials that gives 0 is when a, b, and c are 0. So these are linearly independent. And in a vector space of dimension 3, every set of 3 linearly independent vectors is a basis. Right? And again, it's because every linearly independent set of vectors can be extended to a basis. So if you have three linearly independent vectors, you extend it to a basis, but you can't have more than three vectors in the basis. So those are the three vectors you started with. Right? So we actually have two symmetric statement. Let me write down to be, so everything is explicit. In a vector space V of dimension n, every set of n linearly independent vectors is a basis. And every spanning set of n vectors is also this. All right. There's just one more result that I need to prove today, and that's the following, which is very interesting and is similar to a statement that you might prove in set theory. So in set theory, suppose you have sets S and T, then S union T, this is union, is the set of all X such that X is in S or X is in T, and S intersect T, the symbol intersect, is the set of all X such that X is in S and X T. So if you draw what's called the Venn diagram of this, the picture, suppose this is a set S is a set T. What's in union is everything that's in one or the other or both. And what's in the intersection, that's everything which is in both of them. So the orange is the intersection, and everything shaded in is the union. And if the sets S and T are finite, then if we write absolute value signs around a set to mean the number of elements in the set, the number of elements in S plus the number of elements in T is equal to the number of elements in the union of S and T plus the number of elements in the intersection. Right? Or an equivalent way of writing that is the number of elements in the union is the number of elements plus the number of elements T, but then you've doubled the number of elements in both, so you subtract the numbers in the intersection. So this is a simple bit of combinatorics involving union and intersection of finite sets, and it's interesting that a similar result is true when you take the sum and intersection of subspaces. So this is section 2.43, and it says the following. if U1 and U2 are subspaces of a finite dimensional vector space V, then I take the sum of the subspaces, U plus one plus U2. So that's a subspace of dimension. There's the dimension of U1, the dimension of U2. The intersection of two subspaces is a subspace space. So analogous to the result for sets, dimension of the sum of the subspaces is the dimension of the first plus the dimension of the second minus the dimension of the intersection. So you can almost think of this as something with a Venn diagram. Maybe this is U1, this is U2. The whole thing together would be U1 plus U2. And where they intersect, that's U1 intersect U2. So you could say the following, this is a proof. Let M be the dimension of U1 intersect U2. This part here. So let's say as a basis U1, U2 up to the use of M. And this is some basis for U1 intersect U2. Now that's contained in U1. So this list of vectors extends to a basis for U1. Say it's U1, U2 up to U sub M. And then we add some vectors, say V1 up to V sub J. So this is a basis for U1. But we can also take U1, U2 up to U sub M and extend it W1 up to WK, which is a basis for U2. So every vector in U1 is a linear combination of these. Every vector in U2 is a linear combination of these. So take the union of all these vectors. I have U1 to U sub M, V1 up to V sub J, W1 up to W sub A. This is a spanning set for U1 to U2. Because every vector in U1 and U2 is this vectors in a linear combination of vectors here, and so yeah. So what we can say from this is the dimension of U1, the dimension of U1 intersect U2 was M. The dimension of U1 is M plus J. The dimension of U2 is M plus K. And the dimension of U1 plus U is spanned by a set of M plus J plus K vectors. So it's in most M plus J plus K. But in fact, I claim that the dimension of U1 plus U2 is equal to MJ plus K. Exactly. So we must show that the set of vectors U up to U, V1 up to Vj, V1 up to W sub K is linearly independent. So suppose we have some linear combination of these vectors equal to 0. A1 U1 but dot plus AM U sub M plus B1 V1 up to B sub J V sub J plus C1 W1 up to CK WWK 0. But if it's the case, if I bring all this from one side of the equation there, I C1 W1 up to CK WWK equals minus 1 U1. These are minus signs, since I'm bringing this to the other side of the equation. Minus AM UM minus B1 V1 minus BJ VJ J. But this is a vector in W in U2, and this is a vector in U1. So this vector is in U1 intersect U2. It's in both. But then C1W1 up to CKWK, if it's in the intersection, it's a linear combination of these U's. It's D1 up to D sub M, U sub M. So if I substitute this in here, I get D1 U1 up to D sub M U sub M equals minus A1 U1 minus AM minus B1 V1 minus BJ VJ this is a vector in U1. And in U1, a basis are the U's and the V's. So there must be a unique linear combination. That means all the B's have to be equal to 0. All these are equal to 0. And not only that, but we have the C1W1 is equal to this, but this is equal to this D1 up to DM. So let me just write that out. It's all done very legibly in the book. This says that C1W1 up to CKWK equals D1U1 up to DM U sub M. But the U's and the W's together are linearly independent. So all the C's are equal to 0. And all the B's are equal to 0. So all the A's are equal to 0, just from this equation. Oh, well, this is linear algebra. So once you understand what you're doing, you do it. But to understand what's done does take a lot of time and a lot of work. And I don't know any shortcut for doing the work. But this proves the result that when you have subspaces U1 and U2 of a vector space, the dimension of the sum of the two subspaces is the sum of their dimensions minus the dimension of their intersection. And that's the last result in section 2C. Let me just do one of the exercises. This is on page 48. Exercise 2. It says show that the subspaces of R2 are precisely 0, R2, all lines through the origin. So R2, you know, it's just the ordinary plane. And 0 is a subspace. We say that 0 has dimension 0. R2 is the whole vector space, is a subspace of R2 of dimension 2. If you take any subspace of dimension 2, it's all of R2. This is a subspace of dimension 0. This is a subspace of dimension 2. What is a subspace of dimension 1? So U, if it's a subspace of dimension 1, it has a basis consisting of one vector, V1, not equal to 0. And so U is the set of all scalar multiples of U1. So if this is the vector if this is the non-zero vector V1, the scalar multiples of V1, that's just the line through the origin in the direction V1. This is, and conversely, if you take any line through the origin, take any vector on that line different from 0, the line consists of all scalar multiples of that vector. That's what it is. So in R2, you have subspace dimensions 0, 1, and 2. The only subspace dimension 2 is the whole vector space. The only subspace of dimension 0 is the origin, just 0. And the one-dimensional subspaces are lines to origin. In R3, the subspaces would be 0, all of R3, any line through the origin, and the two-dimensional subspaces would be planes go through the origin. So a plane in R3 is a two-dimensional subspace, a plane that goes through the origin is a two-dimensional subspace, and every two-dimensional subspace is a plane that goes through the origin. Has to go through the origin because every subspace contains 0. Okay, we are moving along here at a nice pace, but that just means there's a lot of work to do. So I have office hours this week on Zoom, Monday, that's today, Monday, Tuesday, and Thursday, 1:30. And if you have questions about the theory in linear algebra, the example, any of the homework problems, then I encourage you to go online and ask me about them. Okay. That's all to do today. Any questions before we go? Next slide. So everyone stay warm and Well, everyone, happy Valentine's Day.
Happy
We'll be-
Valentine's Day, Professor.
Have a great day, Professor.
Thank you. We'll be back on Wednesday. But again, 1:30 today and 1:30 today, Wednesday and Thursday, their hours. If you have another class or a conflict at that time and you have questions, just send me an email and I'll set up some additional office hours. That's no problem. All right. Okay. Be well, everyone.
Have a good one, Professor.